Friends, let us continue our discussion on the reactor design case study number 2, namely hydrogenation of oil. Now, last time we mentioned why hydrogenation of oil is important, and when you hydrogenate, essentially the natural oils that you get have lot of di-unsaturated fatty acids, and you do not want that, and you want to hydrogenate it to get monounsaturated as well as saturated fatty acids. Now, it turns out that as far as the final product is concerned, you do require some polyunsaturated fatty acids, and that is from the health perspective, as well as you require some monounsaturates as well from the consistency and higher melting point of view, which means that if we are trying to hydrogenate the di-unsaturated to completely saturated, that is not what our market demands, and so we have to keep that aspect in mind while designing the reactor. So, let us start our discussion by looking at what exactly is happening when we are trying to hydrogenate this oil. So, we can represent our reaction scheme. For example, let us say this is my di-unsaturated, okay, B. So, in the first set of reactions, that is where hydrogen is added, we get monounsaturated, and this is a cis form of monounsaturated, and we have an trans form, it is isomer. So, we have cis and trans. So, once again plus H2, and there can be an isomerization between these two forms, and these in turn gets further hydrogenated. So, let us say plus H2 to give fully saturated fatty acids. So, the species that are of interest to us are this B di-unsaturated, R1, R2 monounsaturated fatty acids, and S saturated fatty acids, as well as hydrogen. Now, I also mentioned that this reaction takes place in presence of catalyst, and Raney nickel or nickel in a micron size particles is often used as the catalyst. So, design of this reactor therefore involves looking at solid, liquid and gas reactor, and slurry reactors are most commonly used, or in other words we have a stirred tank reactor in which let us say oil is present, a batch reactor we are talking about. So, there is no addition or removal of oil, but we are continuously bubbling hydrogen, and there are catalyst particles because of which these set of reactions are taking place. So, now let us start our discussion on designing this reactor by looking at kinetics of this process. So, our first task is to develop the kinetics, that is not worrying about mass transfer at the present time, and we will worry about the kinetic aspect. So, the first step is, for example, hydrogen gas. So, we will write our mechanism of the reaction, and this is adsorption with dissociation. So, on two active sites, hydrogen molecule gets dissociated into atomic form and occupies each of the active site. So, HL. Similarly, we have let us say B plus L, B is our di-unsaturated, gives us Bl, then Bl plus HL gives us BHL plus L, and BHL plus HL gives us the required product R1L plus L, and R1L dissociates to form R1 plus L. So, what we are looking at is the individual reaction B going to R1, that is the first one of the hydrogenation steps. So, we have adsorption, we have surface reaction, we have desorption. The similar kind of mechanism that we saw earlier when we were discussing the kinetics. So, one can apply quasi steady state or quasi equilibrium approximation. Here quasi equilibrium approximation was applied, and what we get is the rate of this reaction, let us call this as first reaction, is equal to K1 C hydrogen raised to half into Cb after certain simplification. So, this is my reaction 1. If you let us just go back, let us say that this is my reaction 1, reaction 2, reaction 3 and 4, and reactions 5 and 6. Okay. So, I have this reaction mechanism. So, one can write for each of these reactions. Notice here that reactions 1, 2, 5 and 6 are hydrogenation reactions, whereas reactions 3 and 4 are isomerization reactions. Okay. So, what we just wrote was the typical mechanism for isomerization reaction, for hydrogenation reaction, and we get this kind of rate laws. In fact, rate laws for all the 4 reactions R1 to R4 are of the same form, namely these rates being proportional to concentration of hydrogen raised to half and corresponding substrate reactant. Now, we can do the same thing for second set of reactions, namely R1 now binding with L and eventually getting hydrogenated to the saturates. So, if you do that, so if you consider reactions 5 and 6, which were namely R1 to S and R2 to S, we will get rate R5 for example being equal to K5 hydrogen concentration into CR1, and similarly R6 as K6 C hydrogen into Cr2 for these two reactions. Okay. So, we have basically the kinetics of the reaction. Thing to notice here is that my R1, R2, R3, R4, R5, R6 for example, R1 to R6 are my intrinsic kinetic rate expressed as moles per unit volume of liquid per time, and Cr1, Cb, Cs, Cr2 are all concentrations of my different species R1, R2, B and so on. Hydrogen concentration C2 that we have written here is the liquid phase concentration. Okay, that is not the gaseous concentration. So, we need to find that liquid phase concentration. Now, if we look at these rates, and let us go back to our slides. So, Once again, this is my reaction scheme, B going to R1, B going to R2, R1 going to S, R2 going to S, hydrogenation reactions, and then the isomerization reactions. As I said earlier that R1 to R4 are proportional to carbon hydrogen concentration raised to half, and R5 to R6 are proportional to concentration of hydrogen raised to 1/4 raised to 1, sorry. Now, this implies that selectivity of monounsaturates over saturates. So, for example, if you were to look at ratios of R1 to typically that of R5, it will be, for example, let us look at what happens to R1 by R5. Okay. So, if you take this segment B going to R1 going to S, this is my reaction 1, this is my reaction 5. So, what this would imply is that this is K1 hydrogen concentration raised to half Cb, this to R5 is K5 hydrogen concentration Cr1. So, this now we can write as K1 by K5 into Cb by Cr1 into concentration of hydrogen raised to minus 1/2. So, what does it mean? It means that selectivity of R1 over S. Remember, this is the indication of selectivity of that is let us say concentration of R1 over concentration of S, okay, in a crude way, or dCr1 by dCs if you look at the point selectivity. So, now this selectivity is inversely proportional to hydrogen concentration in the liquid phase. Okay. So, what does it mean? It means that if you want higher selectivity of R1 over S, then the concentration of hydrogen should be lower, otherwise you will get results differently. So, let us look at when you actually do batch experiments, how does these results look like in the domain of yield conversion diagram. So, what we are looking at here is the conversion of monounsaturates, conversion of B versus yield of R1, and this is yield of R1 plus R2 put together. Once again, our scheme is these hydrogenation reactions with some isomerization reactions. So, if we look at conversion of B on the x axis against R1, that is on the y axis over here, or R1 plus R2 which is in the second plot, we see the following. As conversion increases, initially the yield increases, okay, because more and more of B goes to R1. But if we wait long enough for entire conversion of B, that is if we go to this point, we see that the yields start decreasing, and that is not what we want. We want certain concentrations of R1 and R2 also in our reactor, or in other words, we are not going to aim at, and we also want certain quantity of B. So, we are not going to aim at 100% conversion of B, but where the optimal yield of R1 is obtained. So, our reactor design Now, desired conversion is not 100% conversion of B, but certain 80% or 70% depending on whatever may be the true results. So, that is point number 1. So, in other words, our x desired is in the range of 0.7 to 0.8. So, we should not design our reactor so that we get 100% conversion. That is one aspect. And other aspect also is apparent in this figure is this particular solid line is the result for, or these two different curves, solid line and dotted line, are results for different RPM. So, let us say the solid line is for RPM 1 and the dotted line is for another agitation rate RPM 2, and it turns out here that RPM 1 is greater than RPM 2, or in other words, solid lines are the results where you have agitated system more and you get or rather you have agitated system less. I stand corrected, these are the results for RPM being less than RPM 2. So, if you agitate more, you get lower yields. Now, at first glance these results may look paradoxical. Generally, we assume that if we agitate system more, you will have uniform mixing and therefore, between the gas phase and the liquid phase, and therefore, you should get better mass transfer and better kinetics or yields or selectivity, whatever we are looking at. While the first part of this is true, that is, you agitate more, you will have better mass transfer between gas phase, that is hydrogen, and the liquid, you will have higher concentrations of hydrogen in the liquid. But as we just now saw a few minutes back, that in order to get higher selectivity or yield of R1 over R2, we need lower hydrogen concentration, because that selectivity was inversely proportional to hydrogen concentration. So, lower RPM, lower hydrogen concentration, higher is the selectivity. So, another lesson that is to be learned from this example is that when you are trying to design heterogeneous reactors, achieving uniformity, highest degree of homogeneity, mass transfer is not necessarily always the design criteria. So, here among the two, RPM 2 or the lower of the RPMs is to be selected, because that gives you higher selectivity. So, this brings us now to what happens to the mass transfer aspect. So, this is as far as the kinetics is concerned. So, let us go back and look at how we handle the mass transfer aspects in this system. As I said earlier, we have a gas liquid solid system. So, here is my solid catalyst, nickel catalyst, here is my gas phase, and separating the two is the liquid. So, now for this reaction to take place, the following things must happen. Hydrogen is over here, my oils are over here, and this is my nickel catalyst. So, the reaction has to occur by interaction with the catalyst. So, in other words, hydrogen has to get transported from the gas phase to liquid phase. So, gas liquid mass transfer, then in the bulk due to the motion of agitation, then to the catalyst, and then further reaction in presence of the catalyst. Or in other words, we have now 3-step process, of which important are these two mass transfer processes. Okay. So, now to handle these processes, now we have a gas liquid reaction. So, let us say that we now represent this by assuming that there is this is a gas liquid interface. We will analyze this situation in the framework of two film theory. So, let us say that this is my concentration of hydrogen in the bulk gas phase. I am going to neglect the gas side mass transfer resistance and assume that the concentration in the bulk is same as the concentration at the interface. Then due to mass transfer interface, concentration drops down, and let us say that this is my concentration C2L, okay, in the liquid. In the bulk liquid, the resistance is negligible. So, we say that the concentration is same as C2HL, and then once again this is my solid interface, and again mass transfer resistance, and this concentration is concentration of hydrogen on the solid surface. So, once again I repeat, we have two interfaces, gas liquid and liquid solid, and therefore, two mass transfer resistances, namely from the bulk gas to the bulk liquid, all mass transfer in this thin film. Bulk liquid transport is or mixing is good. So, we do not assume any further drop, and but from the bulk liquid or the again bulk liquid to the solid, entire mass transfer in this boundary layer, and we have concentration C2S. Now, all the kinetics that we wrote, that is R1, R2 and so on, we said R1 is proportional to CH2 raised to half. That concentration must be concentration on the surface of the catalyst. Now, here once again we are going to make another assumption. Typically, what is seen is that this is a micron size particle and these are millimeter size bubbles. So, gas bubble is typically much bigger than the particle. Particle is really micron size. So, diffusion of oil in the nickel particle, as it is, it will be a tough proposition. So, whatever is the reaction occurs at the surface of the nickel catalyst, and therefore, corresponding surface concentrations are what determines the kinetics. So, now let us try to write down the mass balance equations for these processes by looking at first gas liquid interface. So, what is happening at gas liquid interface? The rate at which hydrogen is getting transferred across the gas liquid interface can be represented as KL into AV into CH2 bulk minus CH2L. The concentration difference between these two levels is my driving force, and that driving force times the area available for the area available for mass transfer. So, AV. So, AV here is the surface area of the bubble per unit volume of the liquid, okay, and KL is the mass transfer coefficient. Similarly, what happens at the liquid solid interface? We can write this as once again the driving force for mass transfer, the concentration gradient between the interface or the film and this interface. So, times the area. So, AC is the area of the catalyst per unit volume of the liquid, because we want to maintain all rates in terms of volume of the liquid. Okay. So, now let us write down the mass balance for the bulk liquid. So, for example, bulk liquid mass balance, assuming the volume is V3 CH2 liquid ddt, must be the rate at which gas hydrogen is coming from the gas phase to the liquid, minus the rate at which it is going from the liquid to the surface of the catalyst. So, this is my mass balance equation for the liquid. Okay. Now, let us write down the similar balance for the concentration on the surface, and this must be again this is the rate at which hydrogen from the bulk liquid is coming to the surface, plus the rate at which hydrogen is getting generated at the surface. This must be the rate at which my hydrogen is getting accumulated. Now, I am expressing my rate in terms of volume of the bulk liquid. So, now if we look at this solid balance, if you look at the balance of hydrogen on the solid, so we can take V2 by V3 over here and remove V3, and now we see that V2 by V3, what is V2? V2 is the volume of the catalyst, which will be much smaller than volume fraction as compared to the bulk liquid. So, we can assume that this is close to 0, and the rate of mass transfer Ks AC into CH2L minus CH2S must be equal to minus RH. Now, what is RH? Remember, if we go back to our reaction scheme over here, then the rate of hydrogen generation, of course, it will be consumption in this particular case, must be minus R1 plus R2 plus R5 plus R6, right, because that is the reactions R1, 2, 5 and 6 are the reactions in which hydrogen is consumed. So, the net rate of hydrogen consumption must be summation of all these rates. Okay. So, now going back to our set of mass balance equations. So, what we have first is Ks AC into CH2L minus CH2S is, now I will just write this, I know what this RH is, but this has CH2S into it. So, that is in terms of hydrogen concentration at the surface. Okay. So, now in other words, we know concentration of hydrogen on the surface in terms of concentration of hydrogen in the bulk liquid, but we do not know what is the concentration of hydrogen in the bulk liquid. Okay. That is not very difficult. We have already written a mass balance equation for that. So, in this mass balance equation, for example, I can just simply substitute this for RHS, but we can also make an further assumption, that is the due to the dynamics of mass transfer, this accumulation of hydrogen in the bulk is 0, or it has reached a what we can call a quasi steady state, or in other words dCH2 dt is close to 0. So, if we set this term equal to 0, then from this mass balance equation on bulk hydrogen, we will get KL AV into CH2 bulk minus CH2L equal to Ks AC into CH2L minus CH2S equal to minus RH from these two balances, right. So, we have two relationships now, and therefore, we can eliminate, for example. So, we have three concentrations of hydrogen. Bulk, this will be determined by the partial pressure of hydrogen. Then we have CH2L and we have CH2S, that is on the surface. So, in the gas phase, liquid phase and on the surface, three concentrations, and we can use these relationships to eliminate one in terms of other, and if you do all that exercise, we actually get Ks into AC into CH2L minus CH2S, that is the oxygen transfer across the liquid solid interface, as overall mass transfer coefficient KLa into CH2 bulk minus CH2S. This to you will be somewhat familiar concept, that is, let's go back to this. So, if you look at this is gas liquid and then liquid solid, processes in series, resistances, addition of resistances, and therefore, it is not surprising that we get our overall mass transfer coefficient this is resistance, representation of resistance in terms of gas liquid interface, resistance across liquid solid interface. Once again, what are KL and K? It should be Ks, not Kg. Ks is the mass transfer coefficient across liquid solid interface, KL is the mass transfer coefficient across gas liquid interface, and AV and AC are, AV is the area of the bubbles per unit volume of the liquid, AC is the area of the catalyst per unit volume of the liquid. So, as a result, now we have which is a function of C2S, or in other words, in our kinetics, So, in our kinetics, which we had, for example, what is this value of C2H? That value of C2H at the surface of the catalyst, which we cannot measure, is related to the concentration of hydrogen in the gas phase, in the gas phase CH2B, not a direct relationship, but implicit relationship. So, that is sufficient for us to write down our mass balance equations. So, now the next step of our design would be to write the mass balance equations. What are our mass balance equations? For components in the liquid phase, that is those 4 components B, R1, R2 and S, we have dCj dt equal to Rj, corresponding rates. Then we have this, we just now saw, as a result of assuming steady states for hydrogen concentration in the liquid as well as hydrogen concentration on the surface of the catalyst pellet, and thereby combining these two, we have the final form of this with overall coefficient defined in this manner. So, I can now simulate my reactor if I know the initial concentrations of B, R1, R2, M or saturate S and the hydrogen concentration in the gas phase, because we just now saw that hydrogen concentration in the gas phase is in turn related to the concentration in the liquid. So, how do we go about designing this reactor? So, essentially it is a typical stir tank batch reactor in which we have multiple stirrers, because the height to diameter ratio is not always 1. In fact, that would make the reactor will occupy much more horizontal space. So, it can be the height to diameter ratio can be in excess of 1, typically 2, and in which case we need multiple impellers. So, we have multiple impellers with standard design of their locations, clearances, their diameter vis-a-vis diameter of the vessel and so on. So, now in the design, this is how we can go about designing the process. So, let us recap what we have seen so far before we go on to this process. So, what we had is a hydrogenation of oil, which is a solid liquid gas phase reaction. The kinetics of this process, being a catalytic process, is represented by interaction of the active site of the catalyst with the different species that we have and so on. The mass transfer aspect is represented by assuming the resistance to mass transfer along the thin film which surrounds the interface, particularly on the liquid side between gas liquid and once again on the liquid side between liquid solid, and doing certain manipulations such as steady state assumption and so on, we come up with the mass transfer rates, couple it with the kinetics. So, now let us try to design this reactor. So, as we saw in these results, there were two aspects which came out, that you do not want the conversion to go to 100%. So, you have certain desired conversion in mind. So, with our model on hand, we can now simulate this process and look at what is the time that is required to achieve the desired conversion, and that will fix our batch time. Now, knowing the batch time and knowing the desired production rate, typically you will be asked design 1000 tons per annum or whatever is that quantity, then you will decide on what is the working days, that are available to you, what is the batch time based on these two and the production rate that you have. You will decide how many batches you have to do. Basically, you will do number of batches based on the time available in the year and the batch time. So, that gives you number of batches. You have your total desired production. So, that will give you what should be your production per unit batch, and based on that you will decide on the volume of the reactor. So, here based on desired conversion, we found the time of operation. Based on desired production and the time of operation, we found the volume of the reactor. Now, once you know the volume, then all your either heuristic empirical approach or in today's age CFD simulations or whatever you want to do, one can design the internals, that is what should be the diameter to height to diameter ratio, diameter of the impeller to diameter of the vessel ratio, clearances, baffle sizes and so on. The last thing that one needs to design, because this is an exothermic reaction, and if you go back to our energy balance and the fact that we want to run this as an isothermal reactor, we would like to find out what is the cooling rate that is required, and this cooling rate this has got jumbled up. So, the cooling rate that will be required is minus delta H. This we had done earlier for all the reactions. Each of these reactions will have heat of reaction. So, rate of the reaction into heat of particular reaction summed over all reactions is how much is the energy that is getting liberated, and this has to be removed, and therefore, by knowing what temperature we want to operate this reactor, what coolant we have, we can find out both the area of the mass transfer and AKU, and deciding upon what will be the heat transfer coefficient, we can find out how much area is required. So, that will complete the design of the internals. So, this in short is the kind of exercise that one would have to do if we were designing a batch reactor. The case we saw was the hydrogenation of oil, which was gas liquid solid reaction. So, we have seen two case studies so far. One, reaction in an empty tube or homogeneous gas phase reaction, namely cracking of ethane to ethylene. The second case we just now saw in this session is hydrogenation of oil using nickel catalyst. So, slurry reactor, gas liquid solid reactor, a case in which kinetics, transport, reactor design all come together. Now, let us turn our attention to the another case study, and this case study we will be using extensively for illustrating various aspects of reaction. This is the reaction of ammonia synthesis, a simple reaction. The reaction per se is nitrogen and hydrogen in appropriate stoichiometric quantities give you a mole of ammonia. That is the main reaction. Now, why do we need to synthesize ammonia? There is a tremendous demand for ammonia in fertilizers, chemicals, explosives, polyamides, pharmaceuticals and so on. And typical production sizes are about 150 million tons per annum worldwide, maybe in slightly in excess, but that is the kind of numbers that we are looking at. So, for this reaction, if you look at the reaction. What is happening on the reactant side? We could write this reaction also as N2 plus 3 H2 giving 2 NH3. So, what is happening? There is a decrease in number of moles. So, compared to what we had for ethane cracking, where it was increase in number of moles, here we have decrease in number of moles from 4 to 2. So, thermodynamics immediately tells us that we must use high pressures. The reaction is exothermic. So, once again thermodynamics tells us that lower temperatures will result in higher equilibrium conversion. It is a catalytic reaction where iron or promoted ruthenium, these type of catalysts are used. So, let us look at first the thermodynamic aspect. What we are seeing here is the temperature on the x axis and ammonia mole fraction, that is the equilibrium relationship for different pressures, let us say 1, 2 and so on, and pressure 1 is greater than pressure 2, greater than pressure 3. These are in fact 300 atmospheres, 100 atmospheres and so on. And as we can clearly see that first of all, as temperature is increasing, the equilibrium conversion is decreasing, and this is what is to be expected of an exothermic reaction. We also see that as we increase the pressures, that is equilibrium conversion at 300 atmospheres is higher than 200 atmospheres and so on. So, as we increase the pressures, we are getting higher conversions. So, typical operating conditions that we are looking at is higher pressures and lower temperature. The same effect is also seen from another aspect. If you look at equilibrium ammonia mole fraction versus pressure at different temperatures. So, this is lower temperature T1 to and higher temperature T2, and in general T1 is less than T2. So, as we are increasing the pressure, conversion is increasing, and conversion is also increasing as we are lowering the temperature. So, let us set up the mass balance equations for this particular reactor. Now, what do we have here? We have a fixed bed reactor here, okay, and let us say that we are passing hydrogen and nitrogen here, and ammonia and unreacted nitrogen and hydrogen are coming out of the reactor. There are catalyst particles, and this is a bed of this catalyst particle, and the reaction is taking place. It is an exothermic reaction. So, first I have to set up the mass balance equations for the catalyst. So, if we say that this is my catalyst and concentration inside is C prime, temperature is T prime, and we have several components. So, Ci prime is the concentration of components such as hydrogen, nitrogen, ammonia inside the catalyst pellet. T prime is the temperature, and what is happening? Steady state diffusion and reaction. Okay. This we had seen when we talked about individual catalyst. Similarly, non-isothermal catalyst pellet. So, energy balance, rate of reaction times rate is your conductive heat transfer. So, this is as far as the catalyst is concerned, but the gas is flowing outside this catalyst and the concentrations of the gaseous components are, let us say, Cj. So, we now need to link the flow phenomena in the reactor or transport phenomena in the reactor to the transport phenomena in the catalyst. And the way we do this is, for sake of simplicity, we will use the concept of effectiveness factor. So, if you look at this mass balance equation for a, I am going to assume a plug flow reactor or a plug flow in the fixed bed reactor. So, what we have is, we had seen this earlier. Let us say R of species G, where R j is a function of concentration and temperature in the bulk. But now, I also know that my reaction is not taking place in the bulk. This would have been the case balance if the reaction was taking place in the bulk or at least at the bulk conditions. But the reaction is taking place at concentrations C I prime and T prime, and that is where we bring in the concept of effectiveness factor, and we say that the reaction rate is actually eta times R j of C j and T, and that is that mass balance. What is my eta? Eta is my effectiveness factor, namely R observed to R at bulk conditions. That is, if mass transfer resistances were negligible, the rate should have been the rate at bulk concentration and bulk temperature. So, at bulk C j and bulk temperature would have been the rate. The actual rate is R observed, eta is my effectiveness factor, and therefore, in my balance it is actually nothing but R observed, but that I have related through concept of effectiveness factor. Now, there are two ways one can simulate this. If you know effectiveness factor a priori, put that in, or if you do not know, then at each simulation time step we will have to solve these equations for the catalyst pellet, evaluate the effectiveness factor, or if you do not want to evaluate effectiveness factor, just evaluate rate, average rate, right. That is my observed rate is, that is, there is some rate associated with these concentrations and temperature, averaged over the entire volume of the catalyst pellet is my observed rate. So, this is how I would simulate the ammonia synthesis reactor. We will stop here for this session and start looking at how this reactor behaves when we try to simulate this reactor, a non-isothermal reactor, a fixed bed non-isothermal reactor for ammonia synthesis. So, that is what will be our topic of discussion for the next session. Thank you.